Hello friends, I am Nikita and you are watching Prepare for KEET. In this lecture tutorials, we are going to talk about digital communication, the modulation and demodulation techniques, and other various parameters such as bandwidth, SNR and BER. The topic to be discussed will be the introduction to digital communication, modulation schemes such as PCM, DPCM, DM, ATM, ASK, FSK, PSK, probability of error and match filter. Analog versus digital communication. Why there was a need when we already have analog communication to switch to digital communication. So you can see over here that because of the presence of noise in channel, the signal gets easily distorted, and that means AM signal gets. The modulation scheme strengthens the signal, making it more rugged towards channel noise. The signal is preserved as long as the noise and the distortion are within limits. Mostly in digital communication, we use regenerative repeaters, and in analog communication, we just use moreover and modulation scheme to strengthen the signal in the midway. What's the difference between both of them? The devices used to strengthen the analog communication not only strengthens the signal but also the noise. However, in regenerative repeaters, it's just like again a modulator attached with a demodulator. So in that scenario, it will modulate only the signal with sync, only that frequency will sync with the oscillator's frequency and demodulate every other frequencies, thus being a greater reliability. Analog messages such as photocopies, films lose quality to successive stage of reproduction. However, such scenarios are not there in digital. Moving further, to represent a digital signal, there are numerous other line codes such as polar, unipolar, bipolar, split phase, Manchester. Now the difference in all of these are that polar for a 0 pulse will be given by a 0, and for pulse 1 will be represented by A magnitude. So if one have some magnitude A and pulse Z and 0 and non-polar are represented by A for pulse 1 and minus A for 0. For polar return to Z, we have the same pulses but for Tb/2 duration, and similarly rest for all. Here you can see the power spectral densities of all signals Sy of f when these are multiplied with the pulse of unipolar signals. Okay, you need to understand that there is two combination. One is the pulse multiplies some magnitude. Okay, and this is the essential bandwidth. That means polar signal requires the maximum bandwidth, which is 2 into RB, and other unipolar and bipolar requires only RB bandwidth. Now moving to the modulation scheme. Digital modulation pulse scheme does sampling, quantizing and coding to convert analog waveform into digital waveform. We know why we do it, but how we do it, we are looking at that. First one in this scenario is pulse code modulation. This modulation scheme works having an analog to digital converter, a transmitter and digital to analog converter at receiver. At transmitter end, the signal gets quantized into L level. Let me show you. Suppose this is a sort of signal. So you can see that what quantizing a level means. These are the different levels which I have demarcated on y-axis, and at x-axis for a particular instant of time, whatever the signal value comes, which is nearest possible to the y value will be its value, will be its quantized value. The quantized value for an encoder, okay. So where we were, an encoder translates the quantized samples into digital code words. For v bit, log s to the l, s to l, that means 2 to the power, l is equals to 2 to the power v, where v is the number of bits and l is the number of levels. A signal is sampled at frequency fs is equals to 2v according to the Nyquist rate, and sometimes it is sometimes the signaling rate is twice of fs, or signaling rate is v into fs. Okay, as I have taken that the transmission bandwidth will be half of the signaling rate. So keep in mind that how to calculate number of levels, what will be the sampling frequency, what will be the transmission bandwidth. These are very important because sometimes in question they ask you about the transmission bandwidth. Now this, for a better clarity, this is a block diagram for PCM signal, a source of continuous time message signal and passed through a low pass filter, then sampled and quantized, like sampled on x-axis, quantized against y-axis, and encoded and sent to the channel. Over the channel, it faces many regenerative repeaters, and at the receiver, a regeneration circuit followed by a decoder, reconstruction filter, and you have reached your destination. So this is the complete view of PCM modulation, demodulation, and over its transmission path. The quantization noise is often calculated as 3L square, and the destination to noise power. Now this is a very important value because many a times they will ask you to give the number of bits according to S signal to noise ratio. Okay, if SNR is equals to 4.8 plus 6 in dB and its unit is dB, that you need to know. Always remember that SNR is calculated in digital communication in decibels. Let's look at one on 2017 question. A sinusoidal message signal is converted to a PCM signal using a uniform quantizer. The required signal to quantization noise SQNR at the output of the quantizer is 40 dB. The minimum number of bits per sample needed to achieve the desired SQNR will be, so the maximum amplitude value is A. Let's suppose we have divided the whole signal into L levels. Number of bits to represent that L level is V. Then the step size will be equal to 2 into A by L. Signal power is A square by 2. Here it should be 12. The quantization noise is always del square by 12. If you put the V value in this del value, then you will see it will be 4A square by L square into 12, right? So we get this value. SNR at receiver is this, and we take its logarithmic calculations and we get this value, that is 1.8 plus 6.02 into V. So you cannot say that for every other quantization formula that SNR is equals to 4.8 plus 6V. It varies according to the signal. If your signal is a sinusoidal signal, then your quantization noise will be 1.8 plus 6.02 dB. According to that, it will be 7 bits. However, accidentally, if you put the earlier formula, you will get number of bits equals to 6, which will make your answer completely wrong. So be very careful in reading the questions. Moving on to our differential pulse code modulation technique. How it is different from pulse code modulation, and that will give you the idea that why there was a need for DPCM. In DPCM, neighboring sample is taken with the reference signal. Difference error is quantized and encoded. EK of TS is the quantized error, which is calculated by subtracting the original value minus the quantized value, giving a quantized error. On receiver, the transmitted signal is added to the predicted value to get the true value. So, in this, what is actually already present is the predictor. A predictor that is going to predict the next value is present at both the sample. At the quantized value, a quantizer quantizes the signal. A predictor checks that is the value of MT is greater or lesser than the quantized MKTS, which is the nearest lesser value is subtracted from the original value to get you an error, and that error is quantized and sent over the medium. Now, what is the need for delta modulation then? A DPCM was differential pulse code modulation with the variable del value, right? With variable quantized value. And in delta modulation, it is the simplest because it is just 1 bit DPCM. It always have a comparator and keeps on adding the value or subtracting plus minus 1 in the existing sample value. So DM signal will moreover depends on your present value and add a step size to already existing value. It will always have a constant del value. It will always have a constant del value or only 1 plus minus 1 bit. Now this is the simplest and easiest way of delta modulation. However, it has its own drawbacks. The problem is with the delta modulation is one is the slope overload noise and other is the granular noise. It occurs when the step size is too small to follow a steep segment of input waveform. Whenever there is a steep rise in the signal, there will always be a gradual increase in delta modulation signal. Okay. And whenever there will be a flat surface, it will mostly be hunting around at that signal, which is relatively flat of the input function, and this will consume a lot of noise. Now to solve slope overload problem, differentiate the input signal and equate it. Step size, there should be a divide over here, divided by TS. So that was all about how to convert analog signal into digital signal. But that was analog baseband signal into digital baseband signal. And we have known earlier that the AM signal, which used to be modulated on high frequencies to send it to a larger range. The same problem also arises in digital modulation. That's why digital carrier modulation techniques are followed. To take the signal, digital signal, the quantized digital signal to a larger area. The three digital carrier modulation techniques, which works after the signal being converted from analog to digital signal, or it's a purely digital signal. After that, carrier modulation takes place over it. The carrier is a high frequency signal which have three modulation schemes, that is digital carrier modulation, which is ASK, PSK and FSK. The difference between all of these three is, if we talk about amplitude shift key, then in ASK the binary 1 is represented by a carrier signal and a binary 0 is represented by an absence of carrier. You can say, just like a unipolar digital line code, it works on the same parameter. You can see how it is represented. Here it is unipolar coding. Now the relation between FC and TB. So FC is equals to 2 into RB. That is important. You must know what is the bandwidth. The bandwidth of each and every carrier modulation and modulation techniques. Now the ASK receiver is a square law detector with low pass filter and a comparator with a voltage limiter, and you get your digital signal output. There is null quadrature null effect, by which the signal is often effective. If phi is 90 degree, then the defective signal will become 0, because it adds a parameter of cos phi with AC square by 2, which could make it to change its amplitude. Now the transmission bandwidth for ASK will be 2 RB. Here you can see in the diagram that suppose it is a pulse signal and it is the same signal in frequency domain. Then to calculate its bandwidth at FC, it will be 2 by TB, which is 2 RB. It is done like this. It is an anti-signal and the channel bandwidth is 2 RB. Now energy per bit. Remember these formulas very well, because in now times they often ask 1 or 2 questions from energy per bit, how to calculate BER, bit error rate. How to calculate that you must know very thoroughly, and error probability. So let me tell you about this diagram. A point is always represented by bit error rate, which is equals to AC square TB by 2, calculated by this formula, energy formula, 0 to 2 pi, square of the signal, you get the signal. I guess it's TB, it's TB, okay, it's TB. And the distance between the two signaling point is equals to under root EB. Under root EB, remember this. So the distance between two signaling points, which could be the AC, amplitude of that signal, is under root EB. For till now, I have just shown you the parameters, that it's under root EB and S2. These are the two signals, which is 0, S2 is 0 and S1 is under root EB. Phase shift key. Phase shift key, binary 1 is represented by presence of carrier and binary 0 is represented by a phase shift of carrier. By a pi, actually it is represented, if you add cos 2 pi FCT plus pi, then it will be minus cos 2 pi FCT. This minus is get by a phase shift. This is the modulator. Now the phase shift is often represented with a phase shift. This is a phase shift, you can see in the diagram clearly. from 0 to 1 and from 1 to 0. Okay, from 0 to 1 to 1 to 0. From 0 to 1, from 1 to 0. Now again its bandwidth is 2 RB. The output of the low pass filter on detection is AC square by 2 and minus AC square by 2. Even in this case, it is affected by the quadrature null effect. The bandwidth 2 RB. Energy bit is, in this case you can see that for PSK you have both the signals S1 and S2, and the distance is twice of under root of EB. Remember, for PSK it's twice of under root EB. The distance is twice of under root EB. Twice of under root EB. For ASK it was just EB, but for PSK it is twice of under root EB. With frequency shift keying, the binary 1 is represented by high frequency and binary 0 by low frequency. For FSK generation, NRZ polar coding will be used. You can see that in this scenario, you have AC cos 2 pi F1t and minus AC cos 2 pi F2. Two different frequencies are used to represent a data. Now the output filter will be, I don't think so, this will come, this won't come. Okay. So it will be AC square by 2 pi AC square cos 2 pi F1t cos 2 pi F2t, and the bandwidth will be F1 minus F2 plus 2 RB. Here I wish to tell you that if you wish to know a signal or that both the signal are orthogonal, then you can calculate F1 minus F0 is equals to N R by. Why I am giving you this formula is to calculate RB, bit error rate of a FSK signal having two different frequencies. You can calculate the bit error rate. It is asked sometimes. Actually, it was not asked. It was one of the question and test series which was there. So they have given this formula, and this is my handwriting looks just like a QG kid, I guess. But yeah, the formula is actually for orthogonal signal, and you will see that in FSK we have two different frequencies, two different signals which are orthogonal to each other in this here. So the signals S1 and S2T lies on two different axes, and hence they are orthogonal to each other, and for this reason you use that formula to calculate the bit error rate in a better way. The distance between the two signaling points is under root TEB. So we have discussed that for ASK it's under root EB, for PSK it's 2 under root EB, and for FSK it's under root 2 EB. M array signaling scheme. For M array the channel bandwidth is reduced, which is 2 RB by N. The bit error is reduced by N. The signal energy is N into EB. The distance between the adjacent signaling point, which was 2 into ES sine 2 pi by M, to check for orthogonality that I was talking you about this thing. I was talking you about this thing. If you wish to check for orthogonality, you have to use del of F, which is equal to 2 RB, or in scenarios such as where you don't have a bit equals to 2, you can use it for N RB by 2, where N is the number of. Now this, why I was keep telling you about the bit error and the distances, because this formula will help, because eventually it helps you to calculate probability of error. Okay, now how, first of all, let me go step by step and make you clear that what is probability of error. Probability of error is the probability of getting a wrong bit at the receiver. Suppose you transmitted a 0, you received a 1. or you transmitted a 1, you received a 0. That is, the addition of both the error probability in a binary symmetric channel will give you probability of error. For ASK, the probability of error is dependent on bit energy and the noise. The basic formula, the very basic formula to calculate probability of error is P is equal to Q is a Gaussian signal over here under root. This is the basic formula. Put every other formula into this. Now D minimum, which we have already calculated, for D minimum square will be equals to, in ASK it will be equals to EB, for PSK it will equals to 4EB, for FSK it will be 2EB, right? Where sigma and naught is for noise. Remember, this is for noise and this is for, this is a power, sigma squared is a power spectral density, which will be equals to EB by 2 and naught. If you put all these value, and you will get your bit error and eventually your probability of error for FSK. If you get this value, you put the value of Q in this Gaussian signal. In this Gaussian signal, finally you will get your X value, your mu and sigma will be known to you in the question, and you can calculate the value of probability of error eventually. So this is very important topic, and most of the people get confused in how to calculate probability of error of digital signal, of a carrier modulated signal. And yeah, you just figure it out, go and have a practice on these questions, come back if you have any doubts regarding it. So this is a 2014 question. I was not kidding, okay. These types of questions do come, and you can see that Q be under root of gamma. This is the parameter they are asking us to calculate. Then the value of D. So let me first read the question. Let Q under root Y be the bit error rate, probability of error, of a BPSK over an BPSK, binary phase shift key. Binary means there are two signals, phase shift key, two different signals, over an AWGN channel with two-sided power noise, power spectral density, and not by 2. The gamma is a function of bit energy and the noise power spectral density. A system with two independent and identical AWGN channel with noise, power spectral density, and not by 2 is shown in the figure. The BPSK demodulator receives the output of both the signal. If the BER of the signal is QB under root Y, then the value of B is. First of all, I would like to tell you that having two channels or three channels or multiple channels won't change the BER or X coefficient. Yes, it will have a parameter in multiplication with the whole of Q parameter, but there won't be a change inside that parameter. So to calculate this inside parameter, we already know that power spectral density of noise is N0 by 2. Bit energy is EB. Y will be EB by N. That is already known to us. Now putting the value of PSD is N0 by 2, which is 2 EB under Q. Again, if you put the value in the function, right, it will be under root of 2 EB by N0 Q D of Y. Now I have taken this in a literal sense, like what is Y, not adding any coefficient of it. Then B is equals to under root 2, which is 1.414. As in, do not complicate this, okay? Now if you wish to calculate it with the other formula which I have just mentioned, then you can do it with that formula too, keeping sigma square equals to n naught, you will get your value because it's already the power spectrum. Moving on with match filter. What is match filter? The design of optimum filter to reduce probability of error. Thus QP is minimized, which can be done by shifting the transfer function by sampling instead. The transfer function of match filter HT is PTD minus T, where TD is the time period of that signal. If you see one of the questions which appeared in GATE 2014 is a binary digital communication system which use pulse GT and minus GT for transmitting bits over an AWGN channel. If the receiver used a match filter, which one of the following pulses will get minimum probability of error? The minimum, we have known that minimum probability of error for a BPSK signal is dependent on 2E/N0. Right? For 2E/N0, we know that we need to calculate E energy in all these signals. If we calculate energy in all these signals, you will see that in option A it is 1 and all the rest it is 1/3. So it will be minimum in option A, which has the maximum bit energy. E is maximum, which is option A. Okay. For rest of the, thank you friends. This was all about digital communication. I hope you keep on trying on match filter, bit error rate, about different bandwidth, transmission bandwidth. This is all they ask mostly from digital communication. Practice makes question easier to solve. So thank you friends. If you like this video, subscribe to my channel, press the like button and the bell to keep updated.